In this video, we're going to consider the connection between definite integrals and the area under a curve. And we're going to explore that idea, that connection, by using this example question here. So we'll get to the question itself in a moment, but before we get there, let's consider some of the theory we're going to need to tackle this problem. So first of all, what is the connection between the area under a curve, which is like that shaded area there, and the definite integral, which is a setup like this thing here? So it's quite a straightforward connection. If you take the graph of a function, so I'm just going to make up a function here. So let's say we've got some kind of polynomial function going like this. Let's say this is a function f of x. And let's say we want to define an area underneath that curve, which basically means something like this. You take a couple of lines, these are called they connect to what are called the limits, a and b, and you draw in a shaded area like this. And let's say it's that shaded area that we want to find. If you want to find that shaded area, all you do is set up a definite integral between the two limits, a and b. So that shaded area is trapped between those two limits, the x-axis and the curve. You just set up your definite integral between a and b, so bottom to top, going left to right along the x-axis, of the function f of x, or whatever the function is, dx. And if you evaluate that definite integral, the answer you get, the numerical value, is exactly that shaded area. So let's say, for example, that we had an actual problem here and we worked this definite integral and it came out to be, say, 15, for example. So we've worked through the steps, it's come out to be 15. That 15 is the answer to the evaluation of the integral, but it's also the shaded area. So we can also say the area here is 15, and then because it's an area, we'll call it units squared. So basically there's a direct correlation between the area under a curve and the definite integral you would set up to find that area. The only slight caveat to that is if your shaded area is underneath the x-axis, so that one was above the x-axis, let's say you had, for example, a parabola going like this, and you wanted to find the shaded area here. Let's say again the limits are a and b, and let's call this function g of x. So the process would be very similar, and there's still an almost direct correlation, but there's a little subtlety here. So if we evaluate this integral, so integral between a and b of our function, which is g of x dx, so remember the dx means with respect to x. If you evaluate this, it doesn't quite come out to be the area, but it almost comes out to be the area. So let's say in this case, we evaluated that definite integral, and it came out to be some numerical value, which it would do. Well, that numerical value, if the area is underneath the x-axis, will always come out to be negative. Okay, so let's say this one came out to be negative 10, for example. Well, there's still a direct correlation, or almost direct correlation, to the area, the shaded area. It's just that obviously an area cannot be negative. So all that we do in this case, we say, well, okay, the area is equal to, we just drop the negative and just make it 10 units squared. So you're still getting the same number, you're just basically taking the absolute value of it, or in other words, dropping the negative to make it positive, and you still copy that numerical value. So it's basically the same idea, just with a slight caveat and a little bit of subtlety on the second example. So keeping those two things in mind, let's take a look at our problem over here. So we've got a diagram here, obviously of some kind of cosine function. So taking on the familiar cosine shape, but notice that we don't actually know what the function is precisely. We know it's a variation of cosine with some a value in front, some b value in here, which we're not told. And then we've got to evaluate the integral between 0 and 3 pi by 4 of that function, the same function dx. And we're given this diagram to help us achieve that. So the other piece of information in the question is that the shaded area here, so just this part, not the whole thing, just that part, is 1/2 units squared. So it's a notoriously difficult little problem, this one, even though it's not a big problem and it's not particularly complex, but subtle. It's very subtle, and it helps us draw out some of the issues that the connection between a definite integral and the area present. So the first thought with a question like this would be, okay, well, I just integrate as normal, just evaluate the definite integral as normal. So I would integrate this function, I would sub in my values, and then I get my numerical value. I get my 15 or my 10 or whatever the number is going to be. The problem with that, of course, is that we don't know what the actual function is. We don't know the a and the b values, so we can't just go ahead and integrate, because the integral would still have an a and a b value in it, so that's no use. Now, you can try then to work out the a and the b values, and in fact for the b value you can work it out, because the b value in this scenario, remember, represents the number of cycles of the cosine graph in its period of 360 degrees, or 2 pi radians. Or another way to think of it is that the graph is going to get squished by a certain factor. Whichever way you think of it, this point here, where the graph cuts through the x-axis for the first time, is normally at 90 degrees, or pi by 2 radians. This one's at pi by 4 radians, or 45 degrees. That means the graph's been squished by a factor of 2. That basically means compressed by a factor of 2, not squished. So that means that the b value is 2. In other words, you would get 2 copies of the cosine graph in its period in the range 0 to 360 or 0 to 2 pi. That's great to figure that out, but it doesn't quite help us because we would still need the a value to go with that. Unfortunately, because there's no labels on the y-axis, on the vertical axis, there's no way to work out the a value. So that means that we can't just figure out what the function is and then go ahead and integrate in the normal way. So we need to think of some other approach. And that's really when the connection between the evaluation of a definite integral and the area of a curve, or the area under a curve, comes into play. So we're told that this area here is 1/2. Maybe that's going to help us. We just need to figure out how to tie everything together. Well, we know from the theory over here, there's a direct correlation between the evaluation of a definite integral between two limits and the shaded area. So if we take that sort of approach, then 0 to 3 pi by 4 would basically be this part here plus this part here. Now I'm just going to maybe put a a horizontal shaded area into there. So if we could basically add together those two areas, then that would give us the evaluation of the definite integral, because we know from over here there's a direct correlation. So what I'm saying is, let's transfer the problem and say, well, let's not think about it just as a definite integral, let's think about it as shaded areas, because the two are apparently, according to the theory, one and the same thing. So working that up, then we would get 1/2 for here, this part here, and then we need to consider this part. Well, to consider this part, you would need to know a little bit about the cosine function. The cosine function is symmetrical around a line that goes down through there, and not only is it symmetrical in this part between pi by 4 and 3 pi by 4, but it's also symmetrical in the sense that this part here, this part, and this part are all the same. These are the first three quadrants of the cosine function. The next quadrant carries on up here to 2 pi radians. So in other words, the area there, and there are the same. They're all 1/2. 1/2, 1/2, and 1/2. So therefore we can say that this would be 1/2 plus the next shaded area, which is 1/2, plus the next final shaded area, which is 1/2. So 1/2 plus 1/2 plus 1/2 gives us 1.5, or 3/2. And that's how most students will approach that problem. And it seems to be correct, right? Because we've said that there is this direct correlation. So we're transferring the problem from the definite integral, just thinking of it instead as areas, adding the areas up, and we get 3/2, 1.5. So it's not quite correct, but it's almost correct. It's not correct because, remember what we said over here about the shaded area underneath the x-axis not directly correlating to the evaluation of the definite integral. In other words, if this question had said, what is the shaded area under this curve between 0 and 3 pi by 4, then the answer would definitely be 3/2. In fact, we would write the answer as 3/2 units squared. Now that would be simple geometry, because if that's 1/2, and these are all the same, then you are literally adding the 3/2 together to get 1.5, or 3/2. In that case, we'd be done. But it doesn't quite work like that here because of that issue of these two parts being underneath the axis. Because notice that here, this question is not asking us to work out the shaded area, it's asking us to evaluate a definite integral. Now we know that when we evaluate a definite integral, which is set up to represent an area underneath the x-axis, it will come out to be negative. So this here, I'm just going to park in brackets because it's not actually correct. But taking a similar approach, this part's not a problem because it's above the x-axis. So there's a direct correlation between the integral and the area. So that is 1/2. These guys are 1/2 as an area, but as a definite integral being underneath the x-axis, they would both evaluate to negative 1/2. So it's actually going to be minus 1/2 and then minus 1/2. So the final answer here, these cancel out and you end up getting minus 1/2. The problem with this question is that we're transferring the problem, evaluation of the definite integral, onto the area, which is an absolutely legitimate thing to do. You can work between these two things because they've got that direct correlation that we explored over here. But it's the fact that you switch between an area that's above the x-axis and an area which is below. If it was an area question, you would ignore the fact that it's below and make it positive 1/2 and positive 1/2. But because we're only evaluating an integral, not finding an area, even though they're almost one and the same thing, the final answer here is minus 1/2, which is acceptable for the evaluation of an integral, but it would not be acceptable as an area because you can't have a negative area. So that just helps us explore a little of the connection between definite integrals and areas in both of these scenarios, and how sometimes you've got to transfer one to the other or vice versa, just depending on what the problem is, but also raising the subtlety of how the two go together in an almost seemingly contradictory way. So I hope that makes sense and I hope that helps if you're working definite integrals or areas under curves. If you've got any questions about this video, just leave them in the comments below.